time to start our session. When you looked into the program, you might think that somebody was using Control-C, Control-V, copy-paste, because all the time you are the same speakers. I thought how to entitle this session. I thought it would be good, Michal and friends, yeah, because it's actually such situation. Okay, so we have 4 presentations. The first speaker is Michal Holčapek on inference mechanism on fuzzy probabilistic inference space. Michal, the floor.
Thank you very much, Przemek, for your introduction. Yes, we have here 3 talks, and these talks should present our ongoing research on fuzzy probabilistic inference systems. And because we are still finding new and new problems, and we are trying to solve them, so now we have the opportunity to present partially what we are doing and what we got. So the first talk will be about the inference mechanism for this type of inference systems, which combine 2 phenomena, probability and fuzziness. So, sorry, switcher is not working. It's the standard issue here. The topic will be split it into 3 parts. The first part will be some motivation from regression theory. The second part will be some information and basic concepts from fuzzy probabilistic inference systems. Then I will continue. Before it was working, now it's not working. I will continue with the inference mechanism. It means that if we generate some, say, quantile functions, you will see later. So then we would like to generate another quantile functions for different points. And this is about inference mechanism. Then I will show you some examples. And okay, so I will wait. It was working before. I tried, but now when we are connecting online, so it stops to work. Fuzzy and probabilistic, so it means that if-then rules are designed that in antecedent we consider fuzzy sets to provide some partition of the space. And in the consequence, we consider probabilistic measures expressed using quantile functions, because there is like relation, one-to-one relation between probabilistic functions and quantile functions. So, okay, I will skip it. First, something from the quantile, from the regression. Well-known regression is ordinary least square regression. The regression function is designed to estimate the conditional mean. So if we consider this type of function, so the parameter vector beta is estimated in this way. So we consider least square here. If we consider, because this least square regression has some problems with biases, outliers, and so on, we can use another type of regression, which is called quantile regression. And quantile regression is defined in the way that the regression function from some q is from this unit interval, is designed to estimate the conditional distribution expressed as a quantile function. So it means that we have this type of distribution. And the parameter vector beta q is another parameter, is the probability, is estimated from a sample in this way, where rho is the loss function defined in this simple way. So we have like q and 1 minus q in this term. And we are looking for beta minimizing this term. This it means that if we would like to find similarly like for the standard regression, the quantile regression, we can consider the function along the whole axis x to estimate, say, the layer of the conditional distribution for fixed q. For example, median function. Yeah, but we can even rho q is loss function. No. This is not bell-shaped. It switches between two values, q and 1 minus q for u. So it is less than 0. So we use here 1 minus q, and it's greater q. So it's like switching between these. Some generalization for that, because we have just one type of function for any q. We can look on some like local determination of this function, which is provided by kernel quantile regression. You have some kernel, so it means function which is very similar to the basic function in fuzzy partition, for example, Gaussian kernel or triangle kernel and so on. So we can determine locally the function which is related to a fixed covariate x0 from x in the way that the parameters are determined almost in the same way like for quantile regression, but multiplied by weights. Weights are determined from the kernel. And the result for fixed covariate x0 is obtained, so quantile value of the quantile function for x0 is obtained like the value for the determined function when we found the beta parameter for q. It's time consuming. x0 is like a node for fuzzy for basic function. This is like central point for this kernel. For central point for this kernel, it means that for any x0 and for any q, we determine these parameters, and we substitute x0 to this function, and we get the value of the quantile for q. It's time consuming, really, because you have many x's, so in that way, so we are just tuning and tuning. Just a note, g is usually linear function in practice. Yeah, not polynomial, but linear. It's almost sufficient here. Here is the literature about this, and I will go to fuzzy probabilistic inference system. Fuzzy probabilistic inference system is a system of if-then rules. When in the antecedent we have fuzzy sets, in the consequence we have quantiles describing the distribution of some random variable y. So x is a real function, x is a real variable, and y is the random variable. So this is like the relation between two worlds of the standard real values and the world of random variables. And AK form a fuzzy partition of some input space, x, usually real numbers. QKQ is a weighted conditional quantile function y given AK, something like conditional with respect to this fuzzy set. And in the same way, like for kernel quantile regression, we can determine this function, but here we consider the constant. So g is now the constant function, not the linear function, but the constant function. So we are looking for the constant, and this constant, say the quantile, the q-weighted quantile. And the weights instead of kernel are now replaced by the weights from fuzzy sets from fuzzy partition. So for any k, which k is related to some node, some central point of the basic function, we can determine using this way distribution function or a probability function. Now the question is, okay, we can find it for all fuzzy sets, for all nodes in the same way like for fuzzy transform. So now the question is how to determine the distribution function for any x from the space X, capital X. We use some inference mechanism, and the first motivation was, okay, we use the same approach like fuzzy transform, quantile fuzzy transform. So we consider weighted average of quantile functions for given Q. And in this way, we find some function that could be like not quantile function, but it could be like the function over all x, which could be somehow like a layer, Q layer for probabilities. Yeah. Here is some example. I will not go to the details, but here is the result. This is the quantile function for some k, sorry, for some q. For example, the yellow curve is for q equal to 0.05. This is like percentile. And you can see that the proportion looks very similar to the q. So it means that this is the percentage of observations below the quantile regression curves here. So it means how many points we have below. And you can see that it split the data very, very well. So I will skip this. Our question is the inference mechanism well defined? Because it's somehow like ad hoc. Okay, we just provide some mixture of quantile functions. And is it good or not? Because from the first time, I thought, oh, it's ad hoc. It looks like not so natural. But finally, we found that this is a really natural approach to define this inference mechanism. But we need to go to some deeper theory. This deeper theory is Wasserstein metric space. What is Wasserstein metric space? Wasserstein metric space is a pair of the space of probability measures. Here we consider one-dimensional case satisfying this property. P moments for this probability are finite. And the Wasserstein distance between two probability measures is defined in using integral like infimum over all joint distributions P, whose marginals are probabilities mi and ni. So we are looking, this is called coupling, and we are looking about some transport between two probabilities. Two probabilities, mi and ni, that join these two probabilities. But if we one forget, we get the another one. So it means that these are marginals. It's a well-known concept which is used also in the optimal transport, for example. So, and now in one dimension, the P Wasserstein distance can be computed in this very, say, efficient way. So using quantile functions. So we determine to any probability measure quantile. So it's sufficient to calculate the integral which measure like distance between quantiles over all Q's. Okay, so we have some kind of LP01 metric, and this metric is applied to the distance between these two quantile functions. And using this Wasserstein distance, we can determine Frechet mean, and Frechet mean can be or is defined like Frechet mean of between or Frechet mean for a set of probability measures. So we are looking for a measure which is somehow in the middle between these probability measures. this is the threshold mean, and the threshold mean, which is moreover weighted, can be computed in this way. So we are looking for the measure from this space that the sum using the weights, the distances between considered measures mi, and this measure is minimal, and the result is this probability measure. And what is nice, that this measure can be found like using quantile functions which are exactly linear combinations of quantile functions. So the gamma described here can be found using the weighted average of quantile functions for probability measures mi. Yeah, because the square. Yeah. Now the question is, okay, we somehow justifies the use of that, and also we can generalize it. And just briefly, we can generalize it using, I will skip it, using arbitrary p, because in our case we use p is equal to 2. Now, for example, we can consider p is equal to 1, and we skip to threshold median. So now we have threshold median, but the problem is that for different p, we can get more results, more measures. Yeah, because you remember from maybe secondary school that if we calculate the median or some quantile is not uniquely determined. It depends on the definition. So in the same way, we can get more such quantile functions. So again, I return to this result. What is important here, that the sigma square is a function, not homogeneous. So the randomness or the noise is dynamically changing with the time. And here we have like a comparison between average and median based inferences. You can see that the median is like some step function. If we use the average, so we get some like smoother function, but the results are almost the same, maybe very similar. Here we can look on the comparison between the theoretical variance, and this is the theoretical variance expressed by blue curve. This is the variance sigma square, and this is the estimation of this variance from 5 points or 3 point. Now I don't know exactly. It means that we can estimate it from the quantiles and quartiles. This is the quantile for 0.5, 0.95, and the quartiles. From these 5 points, we can estimate the variance, and you can see, and now we can guess what is better. And here is some like summary. We can compare it using some theoretical mean, sigma, and if we compare, for example, here we get almost the same results, okay, for both. But for example, we have also other criteria like pinball loss or CRPS, continuous rank probability score loss. And we can see that, for example, here, the inference, median-based inference is slightly better. So just we have like two options, and moreover, we can also extend to arbitrary p, but this is like research plan for future. So here we have some open challenges, but I will stop my talk now because of the time is running and we have some technical problems. So.
Are there any questions, comments? Yeah.
Mm-hmm. Mm-hmm.
Yeah, the paper of Luciano Stefanini, in which he compared the influence of various metric spaces. Yeah, he compared L1, mostly L1 and L2 and LP in general, and he came to the conclusion that L2 is the best option.
Oh, it depends. It depends on the situation. Yeah, but yeah, it was mentioned here. This is the paper quantile and expectile. The same can be also developed for L2 norms. For L2 norms, but it's a little crazy to use something like quantiles, but based on L2 norm. Yeah, but why not? So, but if we have more outliers, so I think that maybe this could help for inference. Yeah, because it's more robust quantile approach than the standard L2 approach. So, yeah, generally, probably L2 is the best, but there are many exceptions that L1 could be more profitable.
Any other questions? I have to, when you cite Goera's paper, do you think to try in the future expectiles also?
Not now. Not now. I focused on quantile because I can determine distributions, and I would like to use it to determine distribution in future in time series forecasting, because this is the relevant like concept from the probability, but what expectiles determine? No distribution. This is not distribution. This is some similar, but not distribution.
Yeah.
Therefore, now we are focusing
Popular in economical society, expectiles are
maybe, yeah, but we can do the same like job.
I have one more question, just to clarify situation. Wasserstein barycenter, it is the same as Fresher mean?
Probably yes, but different names. Yeah, because the idea is minimize the distance, minimize with respect to the minimizer with respect to the distance, Wasserstein distance. Therefore, we could call it also Wasserstein mean. Yeah, but also we use the weight, so this is like weighted Wasserstein or Freshet mean. Yeah. But it's really nice, and it's very common in the statistical community.
Wasserstein distance is nearly everywhere.
Yeah.
People started to use it. Yes, it's started very popular. Any other questions? Okay, so thank you once more.
Thank you very much.
We stay in the same area in some sense. The second speaker is Myung Kao. Yeah. If we. Now the title is on data-driven fuzzy partition in the fuzzy probabilistic inference system framework. May we ask?
So, what was yours?
Hello, everyone. We just continue our topic. So still the same topic with fuzzy probabilistic inference system framework, but we focus on the other subtopic. It's about the data-driven fuzzy partition. And doesn't work. I cannot move to the other slide.
Support 0 or 3 with my presentation. Now we need to move this to new screen. Start again.
It's okay. In case I will go fast. Huh? Yeah, it works. Yeah. We wait few minutes. Okay, the content is simple. I think I will skip recalling the fuzzy probabilistic inference system because Michael already mentioned it, but we will go faster. And then we will introduce, this is incomplete work, so we just introduce some criteria how to determine the data-driven fuzzy partition and some illustrative example. Okay, we still focus on the probabilistic fuzzy inference rules with the antecedent fuzzy set, and they form a fuzzy partition. And it has been so far in practice, we use the uniform fuzzy partition, but typically it's originally defined with the fuzzy covering. And the consequence is in the quantiles function, and it determines as the minimizer of this objective function with the loss function as recalled in the previous talk. Okay, this slide just recalling the basic and the inference mechanism. The inference mechanism, as we know, the typical one is the weighted average. Just the weighted average of the components, but there's some alternatives one, but we just tested on the synthetic data. Okay, and this is just the illustration of how the performance of the fuzzy probabilistic inference system. I just take maybe another example than the previous talk, and we can see there is the quantile regression performed by the inference system is nicely split in the data. The simplest way, as we know, is to count the percentage of the points below the curve. And here just take 25% median and 75%, and it is quite close for this example also. So here just 25 fuzzy partition, and this is uniform. Okay, as we can see. What I want to talk is this is some advantage of the inference system we focus on. It can reduce the computational cost, like we just need to compute the local weighted quantiles instead of minimizing quantile regression on the whole domain. And in some papers before is estimate the conditional distributions quite desirable, but as we said, there are several open issues, and really we need to improve it. Previous talks we talk about the alternative inference mechanisms, and in this talk we will talk about the data-driven fuzzy partitions. It means it was the natural question that we have so far used the uniform fuzzy partition. It's quite simple to construct by shifting equally with kernel function, with triangle or something, and it's also attractive. But it was the question that can we construct some rules, some fuzzy partition that can carry some properties of the data, some construction hidden in the data. So is there any kind of construction that reflects the local properties than the uniform or not? So we try 3 criteria. And the first one is quite simple. We based on the limit of the range of the data values. It means, but we need to first predefine a threshold epsilon. We need to limit it. And the goal is to construct the intervals such that the data corresponding with this with such intervals has the limit of the range of the data is doesn't go over the epsilon we define in advance. Sure, the defining the epsilon is another issue, but here we don't focus on epsilon, but we just say the criterion that we will construct the interval such that the maximum of the values minus the minimum of the values is not go over some limit. Okay, and once we define the interval, we just simply construct a triangle fuzzy set with a node at one of the middle points. This is the simple way. And sure, and how we, once we determine, for example, the first interval and how we start with the second interval, which point we will start. So, okay, so here we propose three strategies. We can start it. We can start just the index right after the index of the minimum or the maximum of the current interval. Or we can start right after the index corresponding with the classical median of the current interval. Or instead of the classical median, we can start right after the index of the weighted median in the current interval. It just to reduce, because if we start right after point by point, then we have a lot of intervals and it takes a lot of time to reduce it. So this is for us more appropriate. Okay, so this is the behavior of the first strategy. Okay, you can see it. That's still the first criterion with the first strategy. And how we satisfy with this kind of data-dependent fuzzy partition instead of the uniform one. Do you like it? Yeah, because later it will be similar. Yeah. As you can see, yeah. For example, in this area, we can see the distance between the values is not too much. So it's suitable to have some white triangle, and it's kind of linear increasing. So it's similar to uniform in this area, but in some areas where it's more spreading data, then it's more narrow and it's not uniform, just it's appropriate to the data behavior. We can consider the second strategy with the median when we started point. Here in the middle, we have less, just 3, and even we have more or less in the middle and 2. Okay, this is some evaluation. We need to evaluate how the performance of the such quantile regression. This is how we count the percentage of the point below the curve. It is close to the uniform partition. As you can see, 25%, 50%, 75%. But if we use the other common metrics in the probabilistic and statistic, this I'll compare with the uniform fuzzy partition. The matrix, we can use the quantile loss or the scoring rules, the loss based on the scoring rules or the mean absolute errors of the variance when we compare with the theoretical one. And we can see with the fuzzy data driven partition, it provides better results, smaller results, better method. Just for this particular example, just right now. Okay, the second criterion, instead of take the range, the limit range of the data values, we will focus on the limit variance of the data values. So instead of take the max values minus mean values, we will compute the variance, the standard variance, and just limit it, not over some threshold variance. It's just a modification of the first criteria. And this is how it works. What I can say is similar in this area. Maybe the spreading of the data to the average, the mean is not too big. So if we set up the variance like this, then in this area it's sufficient to have only one fuzzy set. We don't need to have many here. And here the dispersion of the data is too high. I think the variance in this area is quite large, so it's many big here. Okay, again, the evaluation based on the measurement is quite close to the uniform partition. I just run the computation to see the numbers. The third one is quite different. Instead of construction to the left, to the right, intervals by intervals satisfy the range of the values or the variance limit. Now we will focus on the bisection. So we will split half first, and from the left side or right side, we consider criteria to split half again. And the rule, okay, let me read a little bit. So first, we need to assume that some interval is already split to equally half interval. So it's trivial because for the whole domain, first we must force it to split, otherwise we have just one triangle, okay? And the subinterval, consider, for example, the first part, the left one, it is further bisected. It means splitting. If there's significant relative change in the residual variance, so we compute the residual variance of the current interval and the interval we consider to split divided by the residual variance. It's not variance in that one, but the residual when we change it. So if this relative error of the residual variance is is rather big, it means it's greater than some threshold we determine. And also we need a certain size of the cardinality of the interval. If it's too small, we don't need to split. So just intuitive now. For example, we take like the minimum of the cardinality for the interval to be split is minimum is 20, and the errors is 0.8 for the residual variance. You can see first we split half, and from the left side it continues to split half, and then it's not splitting anymore because it's not it doesn't have the big change to compare with the current left intervals. So, but from the right side, because it's more movable, so it split more. And this method will provide us the disjoint set of the subintervals. You can see 1, 2, 3, 4, 5, 6. We have 6 intervals. So just try to put the triangle here. We have 6 fuzzy sets for the partition. So it needs to be overlapped, but for now, it's just illustration. And we can make it overlap by expanding to the next middle point. I think this just a proposal and how it behaves in the syntactic example. The advantage is we will have less number of fuzzy sets, and it's sure it captures some local characteristics, some properties as we want. And if it's less fuzzy set, it less the rules. So I think for inference, it's better to adjust it somehow when we want. When there's a lot of limitation, we need to set up some threshold. It's very sensitive, especially to variance. When you turn up a little bit, turn down, you have totally different partition. And for me, I think because the purpose is to minimizing the loss in the probabilities. It's like quantile loss or spin-ball loss or the CRPS loss. So I want to try to construct the fuzzy partition in that way. It minimizes the loss, so we don't need to. It's that's all. If you have some suggestion.
Any questions, comments?
Dylan?
The problem which you solve is quite similar to the problem which we have already solved with time series. And the problem was to find intervals of monotonous behavior, which is evaluated by some evaluative linguistic expression, like steeply increasing, slightly increasing, stagnating, and so on.
Get it.
And the method is, what is essential is that natural language is used there, so that you obtain a description of the course of the time series. This can be used for finding some important points or structural breaks and so on. And what is problem with you with criterion 1 or 2, you have to specify this epsilon. How and why?
Maybe
that's, you get it only by thumb, nothing else. While our method uses natural language, which is the method how to evaluate this part of the series is somehow determine through the structure of the meaning of the expression.
I get it.
Okay.
Gotcha.
Thank you very much. Really, and this approach interesting. I have maybe 9 philosophical questions. Whether have you tried this in your data-driven partitions? They are sometimes varying. And have you tried whether when we apply to non-stationary time series some simple filtering? Of course, it depends on the non-stationarity. But in some cases, due to some moving averages or even differentiating, you may move to a more stationary. So my question is whether you have explored that probably with this some kind of processing would come to more even partitions. So and whether there's some length or whether can we formulate some properties. So in which cases for the original time series there would be the need of value partition, like data driven, and in some cases not. So
you didn't have any filter.
Yeah, this is a very good idea because some outliers can play or persuade this partition because we have, for example, the range outlier is like out of the common values. So it's very good idea. Maybe some pre-filtering. Start with pre-filtering and then maybe continue with some fractioning of the function. If the slope is too high, so and to capture like the behavior of the function which was filtered before, was the outliers and some say extreme values could like say could provide something which is unrealistic. Yeah, it's very nice point. So we could quite recommend.
I think with the
So
slope
maybe-
is better.
What said, yeah.
With the
There are
slope,
many possibilities how to propose like data-driven partition. But for me, we are talking about artificial intelligence. But what intelligence is behind the uniform classifier? I think that this is that is more intelligent. This is like technical thing. But here we see some dynamics which is copied into fuzzy partition. We can have something more, some additional information. In the same way, like Bill proposed, like of time series using linguistic
language.
terms. Yeah, I think that we are on the same issue. Yeah, and now we should try many of like.
We will try. Yeah, sure.
To find some optimal quantum approaches.
So maybe last suggestion, could you show a picture, one of the last pictures? Could you move? Oh, maybe here. Oh, when I look at this picture, immediately I think about local smoothers. in
Yeah.
the functional regression. And maybe next one. Next back, okay. Oh, and here, for example, it seems, for example, if you use wavelets, yeah, which adapt very well to such places when variance is big and are very smooth when they are not. Yeah, so it resembles like wavelet behavior.
Yeah, it's based on variance, yes.
Uh-huh.
But it's hard to determine the appropriate variance.
Mm-hmm.
Find like sound parts and like increase and decrease parts some high derivatives or small derivatives. Thanks very much.
Okay, so thank you. The next speaker is me. Yeah. Organizer decided to break this session of Osama.
But we'll come back.
Yeah, we'll come back. As I said, it's a break. Yeah. So, oh, it's mine. I always have my special tool. Yeah. Okay. So, yeah, it's better to show. Okay. So the title is Asymptotic Methods in Statistics with Imprecise Data. It's a conference on fuzzy set, but word fuzzy will appear on the last slide. Okay. I hope you'll forgive me, but I'll tell you something about imprecise information, so it somehow works in this era. Oh, it works. Okay, so let's start from motivation. Let me recall an example from that basic course on statistics. Yeah, we have a random sample from normal distribution with known mean, unknown variance. And for example, I am interested in verifying hypothesis about the mean. Yeah, but the mean is mu0 against it's not mu0. And such typical test is I compare the average, which is a good estimator of mu, with a hypothetical mu0. There are some constants here, and provided a null hypothesis holds, it is normally distributed. And if this value is too big with respect to the quantity, I reject hypothesis. Okay, this is a point estimator. Of course, somehow looking on this test, I can construct confidence interval. And this is something classic, yeah? But I have promised to say something about imprecise data. And as we are talking on imprecise data, of course, we laugh at the sets a lot. But for example, for engineers, much natural case is a little bit different. Well, if you have imprecise measurements, if you have vague observations, so not necessarily imprecision made by measurement, but the quantities which are from their nature vague, yeah? Sometimes we want to hide some values because of a privacy, for example. And finally, we sometimes observe a range of values, yeah? For example, the blood pressure during the day, yeah? It makes us some range. And in all these cases, a very simple and natural method of modeling such data are intervals. So we have so-called interval valued data. A natural question arises, can I construct similar tests, completeness intervals for data as for real valued data? Of course, yes. Myself, I have a few years ago also discussed about this topic, but these approaches are mainly based on resampling methods like bootstrap permutations. So next question, and the topic for today is, can we derive desired tools without resampling methods, which are often computationally complex, sometimes time-consuming, and so on and so on. Okay? So I recall some notion about interval valued data, about random intervals. Then I specify hypothesis and model. I show you our suggestion for the mean. I say we because it's a paper prepared together with my student, and then confidence interval and conclusion. So let's go on. This is a family of bounded and closed intervals, okay? Sometimes, very often we specify interval by 8 points, but in statistical framework, we rather prefer a slightly different notation using center point radius, okay? So this is interval defined by borders or endpoints, and middle minus radius, middle plus radius, of course, it is the same, yeah? Why it is more convenient? Because, for example, in simulation and many calculations, here to check this condition is not very useful. And here is much easier because I have arbitrary real random variable, and here I have only to keep it to be non-negative. Well, you know that Minkowski addition, scalar multiplication works for intervals, but unfortunately, this structure with such operation is not linear. We don't have opposite element. So natural suggestion is avoid computing the difference. Yeah. Moreover, another drawback is that this set of data, possible data, is not linearly ordered. But what to do? Well, we have intervals, so now randomness. And again, what is random interval? Random interval is just a mapping where each observation an interval, yeah? And in practice, it's worth to remember that I can look on such mapping actually as on two mappings. One which brings us real value to random variables connected with centers, and this with radius. Okay, and since we will be talking about the mean, I have to define the mean in this framework, and it's Ullmann expectation. And again, I can define it by usual means addressed to lower or upper endpoint or center and radius. Okay, so I prepared from the theoretical point of view to our new constructions, but now 3 remarks, yeah? Firstly, that because of the problems with subtraction, we have to avoid subtracting intervals. As you remember this first idea, I have compared t, my x bar minus mu 0. So it's not this solution. Next, because there are not realistic suitable models for the distribution of random intervals, we have to avoid parametric models. So parametric, yeah, we prefer. But of course, in the non-parametric toolbox, rank methods are most popular, but I cannot use rank because the lack of ranking, natural ranking, yeah. So what can we do, yeah? As I have mentioned, we have many resampling methods, bootstrap, permutation, and so on, but we have also, maybe it's a possibility to use some asymptotic approach, and this is what I try to propose in next slides. Okay, so what do we have? We have a data sample of, it's simple random sample. Simple means all observations are taken from the same distribution and they're independent. And as I say independence, I mean the whole intervals, yeah? So intervals are independent, but maybe between centers and radiuses, there is some dependence. Okay, and my null hypothesis is that the expected value of our interval, random interval, is given fixed interval. Again, it is not so. So such a simple hypothesis. And I'll propose to consider a test and confidence interval construction based on well-known Mahalanobis distance. Yeah, this is a general formula for Mahalanobis distance. Here is a matrix. Yeah, and if this matrix is symmetric and positively defined, this dm is simply the metric, because otherwise not necessarily. What we are mostly used to is if in here we have just the inverse of the covariance matrix. Okay, and I'll later on consider such instructions. Well, so now how to apply this methodology to intervals. Firstly, we have noticed that if I know the center and radius, I know the interval. Okay, so let us consider such CR representation of random interval given by such a vector of 2 random variables. If I have a sample where IID from unknown distribution, I assume that it's a distribution which have a finite mean and covariance matrix. Okay. And what next? We know that X bar, it's a good estimator of this. So mu C, it's X bar C, it's just a simple average of Xi's, and the same here of Xi's, but with R, so this connected with radiuses. Well, and the test idea is to use the distance between this and that. So between these two CR representations. And what do we propose? Let's assume for the moment that we know this covariance matrix. It's not realistic actually, but suppose so, yeah? So our idea for test statistics is to use the square of Mahalanobis distance between CR X bar, CR mu 0 multiplied by n. If I put into detail this, so it looks like that, yeah? We have this vector, and this known matrix. And since it is a distance between what is assumed and what I really observe in some sense, when the difference is too big, I simply have to say that I reject. But the problem is, what does it mean too big, yeah? So the problem is how to find this value. Well, f is unknown, so if not using resampling, I have to try another approach. And what do we want to propose? Under all these assumptions I mentioned before, we can prove that such a vector, if sample size is large enough, is asymptotically normal with the following parameters, yeah? So consequently, if this is a part of my distance, so if I put everything inside and I take n times the square of the distance, we can prove that under H0, so if null hypothesis holds and sample size is large enough, the asymptotic distributions is Chi-square distributions with 2 degrees of freedom. Well, Jan-Sun in her paper proposed a test very similar to our, but based on the following distance, yeah? And it appeared that her construction is a specific case of our construction under such form of covariance matrix. Well, I have assumed known covariance matrix, but as I mentioned, it's a rare case. So what can we do if this unknown? The solution is simple. You have to estimate it, yeah? So it's the natural estimator of covariance matrix. And what can we prove? We can prove using Slutsky theorem and continuous mapping theorem that this construction tends to following random variable. Yeah. So again, we have very similar theorem that our test statistics, now it's here tilde because instead of sigma -1, I have the inverse of the estimator of the matrix, yeah. And again, we have, so what's important, that if I substitute the true value by estimator, again, I obtain the same distribution. But it's not so surprising because in traditional real value statistics, when I substitute known variance by estimator and I assume normality, from normality I go to the student. But if I say, oh, well, I don't know distribution, but I have a sample which is large enough, I again land in normal. So that is why it's not so surprising. Yeah. So in general, wherever I know I not know the true covariance matrix, I reject hypothesis if the value of my statistics is bigger than the respective quantile from Chi-square distribution with 2 degrees of freedom. So we have a test, and we can move to confidence interval. The idea is as follows, maybe just here, that we propose to consider as a confidence region. I specifically say region, not interval, because it will be bigger than interval, yeah? Because it will be an object on a plane. So this confidence interval, confidence region corresponds to the set of all such intervals which are not farther from the point estimator than given value. And this value depends, of course, on alpha. 1 minus alpha is a confidence level. So again, repeating all you know, and remember, I consider the distance between now, as you see, I have modified somehow here because it is our covariance multiplied by some matrix. Here are a little bit moved vectors. Anyway, again, because of this relationship, I can compute what I really need and obtain that this C alpha square is quantile from chi-square distribution. So finally, this is the shape of my confidence interval. Well, maybe let us look on a simple example. Here are 12 intervals, simulated values, yeah, not real data. And what? We have estimated all desired parameters since we have 5% alpha, so 0.95, so this is a desired quantile. N is 12, so if I divide this quantile by 12, I obtain something about 0.8. So my confidence interval is obtained as a set of all intervals which are not more distant from this with respect to Mahalanobis distance than that value. And this is a picture how it looks like. This is X bar. And this area is simply this ellipsoid. And of course, so what it means, how to look like. For example, if my lower bound is 9, the upper bound could be somewhere from there, yeah? In general, for any point, I can also, not for any point, for any data set, I can also consider the projections of this ellipsoid either here or there. In this case, I can obtain, say, one-dimensional confidence intervals, which work as where is my confidence interval for one for lower or upper endpoint when the upper endpoint is arbitrary, yeah. But because of this relationship, of course, this ellipsoid is in some sense more reasonable. Well, to conclude, we have considered sets for constructions for interval data sets. Our constructions are based on Mahalanobis distance, which converges nicely to chi-square distribution. In future, we propose to generalize somehow it to confidence, to fuzzy sets. Of course, still more studies in particular comparisons with, we have just started but not finished, comparisons with this resampling tools we have to be performed. And it's nearly all. Let me only make some advertisement for all of you who are interested in the topics related to probability and statistics in this framework of, or environment, maybe better say, of imprecision, vagueness, and so on and so on. This is a 12th edition of our SMPS conference. This year, it will be organized in a lecture, so all of you are welcome. Thank you very much. Sorry for being a little bit late, please.
In your transformation of two ways how to express fuzzy interval. So in your transformation between two forms of expressing an interval, you had one half naturally occurring, but it was not present in that matrix A, which you used later for the transformation. So I assume that you would get half of the value which was obtained from the previous form. So I'm surprised why the one half disappeared in that matrix A, because it had just unit elements, not one half.
I really don't.
If you go back by one slide, what A is, yes, so you have, what A is, the matrix A, yes, he's here. It's not multiplied by one half to make it get the transformation of between these two.
Yeah, but this 1 minus 1 is because I just want to move from.
Yes, it's the opposite direction. Okay, thank you. Sorry, sorry. Yes. Yes.
Kuhara, yeah, of course, but Kuhara difference can be computed if and only if there is a relationship between radiuses, yeah, so not for each pair. So it's not convenient.
It's not convenient.
It doesn't always exist.
You tested with respect to one value, not interval.
Yeah.
If I understand. So
Yeah, it's interval.
Mu is interval.
Yeah.
Okay. So
it's interval, yeah. Any others? So thank you very much. I again changed my role. And again, a person whom you know, yeah. So Nyun Kao, please, and the same team from Ostrava. And the beginning of the title is as before, so fuzzy probabilistic inference systems, but now based on piecewise linear weighted quantiles. So we modify different part of a solution. Okay, the floor is yours, please. Oh, sorry, it's yours.
Okay. Hello again. We're still in the same topic of fuzzy probabilistic inference system, but a different subtopic with a piecewise linear quantile regression. The content is just first, as usual, we record the system and then the model formulation, and we show the potential use of it. Should I recall again the inference system? Okay, we still work with the rules with the antecedent alpha set, and they form a fuzzy partition. And the consequence will represent for the probability distribution of the response data. And it's represented by the quantile function. That is the point. And the inference mechanism, okay, here I record the weighted average, the typical one. Is the weighted the quantiles.
Sorry for interrupting you, but I'm lost at the slide because in the formula you have some xy appearing just once. So without knowing its meaning, I cannot understand the rest.
Yeah, we assume in the environment of real value time series, X is the subset of the set of discrete values, or small x is subset of R of the real number. in this specific work, X is a subset of R, and Y, for sure, it is real values is a subset of R. But
Well, X is if you don't listen, just one single formula, it doesn't implement the other side.
I'm sorry for this slide because we have the T talks in this section, and I eliminated.
Yeah. We had a like a relationship between X and this is like the real domain and Y is the random part of this. So, and the random part is described using quantile function which represents the distribution. So now we are looking like the relationship between the real and random parts.
It's more specific for this talk is the in time series environment, the real values. Okay, before we give two talks about the inference mechanism with alternative methods and the data-driven fuzzy partitions. And now we will focus on the extensions of the determination of the quantile values in form of the constant to the piecewise linear models. And here I just want to recall, typically we determine the quantile values for a quantile level Q as the minimizer of this objective function. And so far it has been a constant. We just find that. And inspired by the quantile relation in the standard setting, we know that the local linear fitting is often outperform the local constant. So it's very natural to extend it from the constant weighted quantiles to kind of linear model. Okay. And why we don't use here just a pure linear line? Because it's simple. It has been used solved by the linear programming problem, and we don't want it. So we propose another way. It's instead of the pure linear line, we propose the piecewise linear weighted quantile function. And so it instead of using linear programming, the computation is much faster. And okay, we need some definition. It's just a technical problem. Assume we have fuzzy partition on the domain X and quantile level, and we define the center point. CK just understand as a node, and ZQ according to the Q given, it's just the weighted quantile constant. So, and we define the piecewise linear function in the way that it passes this center point. And our purpose is to estimate the left and the right slopes A1 and A2 by minimizing optimization of this objective function. Okay. And now we will solve this. No, this is we have one theorem about this. This is to answer the question, is there always exist the slopes A1 and A2 to satisfy this equation or not? And we can prove it. It always exists the pairs of the slopes to satisfy this minimization. Okay, and this is we propose the algorithm, but not solving by the linear programming problem, but by the derivative. And it's very general steps. We can discuss in detail later. Okay, we have, for example, assume we have the observation data, x, y, 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 sent in this way, and data will fuzzy partition. For each case, we will compute the constant weighted quantile Q, KQ by the right derivative based method. And then we determine the central point. And then the important step is we make the transformation of the data. So instead of the xy, yy as the beginning, we will construct, but we distinguish xy from the left side of the node or the x from the right side of the node. We construct different sets of transform data. Okay, by this formula, and after we obtain the transform data, we will apply again the process we compute for the weighted quantile constant. Now we apply for the transform data and obtain from the left slope, the right slope, and from the left side we just take the opposite. This is and this result will minimize the objective function before. This is the process we do it. Okay, and here's the illustration. Clearly you can see this is the constant quantile. Okay, just look in the support of the first set A1. It's around here. I think it's missing the partition here. I don't know why. Okay, and I recall it was here the first partition, but now it disappeared. This is constant, and this is what we proposed piecewise. And this is we try with the linear programming problem with the numerical minimization. So you see this one it estimates the quantile independently with the input. But for these two, is respect more to the behavior of the data. So it should estimate more accurate the quantiles. Okay, and here just 0.05. We can set up the list of quantile levels. We can see it like this. And why I show this? Because of the crossing problem. As we know that in the quantile regression is the crossing problem we need to solve. We are not sure about it. And similarly for our proposal with piecewise, it can be crossed, but this is you don't see it because we fix it. It's crossing. We don't have the picture of crossing, but it's crossing. This is we already fixed it. I did learn a lot of the pictures, so I lost it somehow, but I know it. Okay, so how to fix it? How to correct it? This is at the node. We know that it's always true. The quantiles are monotonicity increasing, but for any other input, it's not guaranteed about that. To obtain the valid quantile function, it needs to be non-decreasing. It should be, and we just follow the classical linear quantile regression. They usually mention two approaches. Either they impose in the constants about non-crossing during the optimization of the objective function. They just put the constant there, or we apply some post-hoc correction. Okay, so the work is not really too deep, so we apply the second one, the post-hoc correction. And how we adjust it? It is very simple. So we focus on the support of for a certain fuzzy set AK, the left bound, the right bound. So if the quantile levels higher another quantile levels, and we observe the quantile values, if it's really higher according to the levels, then we keep it. But if it's smaller, then we lift it up to be equal to that one, to have the valid quantile function. This is the post-hoc correction. Okay, so now just the illustration of the quantile regression after we correct it. Here is the constant behavior of the quantile regression, and here when we apply the piecewise linear, it's more respect to the change of the data, because in a single fuzzy set, it's already respect to the behavior of data. So non-crossing because we fix it. Okay, so I just want to show how it is better than when we use the constant quantile function. So we can use there are many measures, but we can consider the Bhattacharya distance between the blue one is from the theoretical, okay, always, and the green one is from what we estimate. And we note that we assume the normal distribution, okay, for the simplicity. And you can see when we use the piecewise linear, at many points, this is just an example. It's closer to the theoretically. This is just for one input time. Okay, for whole domain, for whole access of the time, you can see it provides the values. This is the values for the distance between the estimation and theoretical. It provides lower values than when we use the constant. This is average values for the Bhattacharya distance. I think this is at the end. So what is the point of this talk? We propose to extend the constant consequence to the form of piecewise linear, with the star it means already fixed with the non-crossing to obtain the validity of quantiles. And as I mentioned before, why we don't use the pure linear? Because we have compute, and actually in the experiment it's much faster than you use the linear programming. And this is we compute the complexity. As you can see, this is with the linear programming, this square of the log, and this is just nothing. That is out.
Thank you very much. Again, questions, comments? Okay, Rina.
I guess, yeah. Thank you. My guess is as follows. Because the technique is very similar to working with F0 and F1 transform. And then if you compare with, in your terminology, constant and linear regression parts, say, then if you make partition for constant finer, for example, twice, I mean finer than the partition for linear components, then perhaps the estimation will be more or less the same.
Yeah, I think so.
Yeah, you also agree. Yeah, okay,
Yes,
so that's
but,
only guess. Okay, thank you.
Yeah, a comment to this. Unfortunately, usually we don't have enough numbers to calculate these quantiles. So if I propose some like narrower baseline or narrower support for fuzzy sets, so I can compute, for example, from 5 points, the quantiles, and I obtain even worse results, because it doesn't capture like the behavior of that, of the variance in data. Yeah, therefore really linear approach is well common approach in kernel-based quantile regression. And I think that also in our approach can significantly improve the estimation of the distributions. But as I said before, kernel-based quantile regression must calculate at each point for any Q, for any probability, 2 parameters using linear programming, and it takes a time. Therefore, if we propose linear programming used only in several nodes, we save time. And even if we calculate it using the method proposed by Jung, we save even more time. So, and yeah, and that's the point. So if we don't consider continuous functions, we are working with data. Therefore, we need to consider some reasonable size of the bandwidth for these fuzzy sets. That's the point. Yeah.
Could you move to slide 5 for a moment?
Slide 5.
I have a question, suggestion, and maybe it's not reasonable, but for example, you have started from such simplest case, yeah? Then you moved to piecewise linear. And if we put here cubic splines, you will have something smooth.
It's very interesting. Usually not used in the kernel relation, but everything is about the linear programming. So you need to find the parameters of the function, but it could work. I think that it could work.
Maybe not only this cubic spline, but also some regularization, just to obtain not too many elements, to put this regularization here, yeah, in this way. Maybe.
Great remark. Yeah, really. But we are starting from the bottom.
Yeah, of course, it's naturally. Yeah.
If you don't care about the computation cost, we can use linear programming and even
but machines are
the SP line.
So.
Moreover,
to minimize.
this is like a technique, but the technique should have some theoretical background, and this background is well known from the kernel-based quantile regression. For example, what kind of distributions are the parameters A and B? Yeah, because these are also random. So therefore, now we would like to follow this theory, but probably we can join the research and we can look at on other kind of functions that can be used inside of this formula, and what kind of distributions have this. Have these parameters, because this is also important. Usually asymptotic, therefore I like your presentation.
Any other questions? If not, thank you very much. Participants, audience, and please enjoy your grants.
Thank you.
That's tricky. Yeah.